Okay, welcome to Euler's method. Euler's method is used to approximate a differential equation. When you take differential equations, you will get more techniques to solve differential equations. But at this moment, there are several equations that we just can't solve right now. We don't have the skills to solve. And Euler's method is a way to approximate the solution to a differential equation without actually solving the differential equation. And the way all this method works, it relies on the previous term. So I've sort of given you an example of Euler's method here. We're going to start by finding the initial condition, which is x0. Delta x is the step by which we increase the function. That will either be found or given to us. The smaller the delta x, the more steps we take, the more accurate our answer is, of course. So we start with finding the initial condition using the initial x, and then we add delta x each time to get the next x. The y value is given by the initial y value, or the previous y value, plus delta x, our step, times the function evaluated at your previous x and your previous y. So when you're doing this, you're always looking at the previous x or the previous y. Now, this becomes a lot easier when we just do a couple examples. So let's do an example. Okay, so in this case, our differential equation is x plus y. We don't have the skills right now to solve this. We don't have the skills to separate it and integrate it. You will when you take differential equations. So, and we're given an initial condition of 0, 0, and we want to estimate y at x equals 1 using two steps. Now, what I did not mention here is that our steps have to be equal. So, two equal steps that should read. So, just trying to figure out delta x. If I want to go from 0 to 1 in two equal steps, then my delta x should be, you got it, 0.5. So the way I'm going to write this is I'm going to start with my x values, and I start with my initial condition. Then I am increasing my x by delta x. So my next x would be 0.5, and then the next one would be 1.0. So I've done two steps. Okay? Now the formula says that to get my y value, I start with my previous y value plus delta x, and I evaluate the function, I evaluate the derivative using previous x and previous y. Okay? So, to find my next y, I start by finding my previous y. So in this case, my previous y is 0. My delta x is 0.5. And then I'm evaluating x plus y using previous x and previous y. So that would be my previous x is 0, my previous y is 0. So I get 0 again. Almost seems as if that didn't make any headway there. Okay, so now to find the next one, I start with my previous y. So I'm going to start with 0 again, plus my delta x times, and now I'm evaluating x plus y using my previous x. My previous x is 0.5. My previous y is 0. And that gives me 0.5 times 0.5 is 5 times 5 is 25, so 0.25. Half times a half is the fourth. And that's my final answer, 0.25. Okay? Let's try another one. In this particular case, my delta x, my differential, only has t values or x values. There are no y values in the previous. So I'm always going to use my previous x or previous t value. So this time I want to go 4 steps. Again, it's 4 equal steps. And I'm going from 0 to 1. And I want to go from 0 to 1 in 4 steps. So what should my delta x be? One way to do it is to say from 1 minus 0 over 4. So that gives me a step of 0.25 or a fourth. So I start with my x values or t values and my y values, and I'm starting at 0, 1, because my initial condition is x is 0, y is 1, and I'm increasing that by a fourth each time. Until I get to 1. Okay? All right, so to get my first y, my next y value, I start with my previous y, which is 1, plus my delta, which is 1/4 or 0.25, times the cosine of 2 pi, and I do my previous x. My previous y doesn't matter here, but my previous x is 0. So the cosine of 0 is 1, so this gives me 1.25. Because the cosine of 0 is 1 times the fourth is 0.25, and then I add that. So I do my next value. I take my previous y, my delta x, times the cosine of my previous x value, which would be 2 pi times a fourth. And 2 times a fourth is 1/2, so that's pi over 2. The cosine of pi over 2 is 0, so it's going to be 1.25. So I take my previous y plus my delta x, and now I have the cosine of 2 pi times my previous x value is 1/2. So that gives me the cosine of pi. And the cosine of pi is -1, so that's going to be 1.25 minus a fourth, which is just 1. Okay, so I think I got off a little bit here. Okay, so now I'm doing the next value. So I'm doing 4 steps, so 1, 2, 3, 4. My last step, I take my previous value, 1/4 times the cosine of 2 pi times 3 over 4, which gives me the cosine of 3 pi over 2, and the cosine of 3 pi over 2 is 0, so that gives me, my final answer is 1. Okay, so I hope that makes sense to you. What I would suggest that you do is I would suggest that you pause this video and try the next one, and then come back and see if we get the same answer. Okay, welcome back. So this one, our initial condition is x is 2 when y is 0. We're trying to get to 3, but this time we're told what delta x is 0.5. So that means we're going to do it in 2 steps. So we start at 2, and then we go to 2.5, and then 3.0. Okay, so to get my y's, it's always my previous y plus my delta x, and now I'm evaluating this function using my previous x and my previous y. So that's going to give me 2 over 2 plus 0 over 5. And that gives me 0.5. Okay, so then I take my previous y, my delta x, and then I use my previous x and my previous y. So my previous x would be 2.5. My previous y is 0.5. And if my math is correct, I think my final answer is 1.175. You can check my math on that. Okay? You know, we like to do free response questions, so I would suggest once again that you pause the video, complete the free response question, and then come back and look at the answer. Okay, welcome back. Now, one of the things I wanted to say about this, I'm going to show you the answer in a second, but one thing I want to show you is that on this question, you had to use L'Hopital. You had to use L'Hopital, and you had to show that L'Hopital was applicable. So you had to show that when you do a direct substitution, you have the limit as x approaches 0. Doing a direct substitution gives you f of 0 plus 1 over sine 0. And we're told that f of 0 is -1 So we ended up with 0 over 0. You had to show, now you didn't have to show this extra step in here, but you had to show that you got 0 over 0, that it was indeterminate, and that L'Hopital applied in order to get that point. And then you had to somehow or another say, therefore, using L'Hopital, and then take the derivative of that and get f prime of x over cosine of x. And also, they're very particular about notation. So you want to make sure that you're writing. If you don't write the limit as x approaches 0, they consider that to be wrong. And so to find f prime of 0, we would simply use this expression. So y here is -1. X is 0. All over 1, and that answer is 2. Okay? And then they use Euler's method, so I'm going to show you the answer, and hopefully you got the same answer. If not, you can message me, and we'll talk about it. Okay? That is it for Euler's method, so please watch logistics functions in just a second. Have an amazing rest of your day.